All right, part 6 of this amplifier build. Today what I'm going to do is go over the last revisions, some of the changes in values, and how I mocked up the parts list, and get ready to order these parts to start building the physical product. All right, so if you recall in part 5, what we did was we determined the operating points and values and constructed the SPICE model, refined the third draft, write out the final draft, finalize the values, and finalize the output stage. So that's the last thing I worked on, and I'll do an overview of that today and go over the next step, which would be ordering the parts and start modeling the physical product. So ordering the parts and finalizing the values actually goes together, and that's why we're doing it in that sequence, because as I mentioned in previous videos, sometimes you can only build in accordance to what's on the market, right? So some of the values that you have might change. For instance, this cathode resistor that I might have wanted I believe maybe a 550 ohm. Well, it turns out, the easiest thing to do is get a 600 ohm. Actually put a 500 ohm in series with a 100 ohm to get my 600 ohm, because I need a 5 watt resistor here because of the dissipation, right? So this is going to be dissipating 2.2 watts. So this is also something that is really advantageous for working in SPICE. So you can not only see the signal that comes through the amplifier, but you can also see not only see the signal and the voltages at your points of concern, but you can also see the current draw. So if I go over this resistor, and if you look in the bottom left-hand corner in that window there, you can see that there's a milliamp rating, and then there's a dissipation. So I can actually see how much current is going to be drawn on the cathode and dissipated from that resistor before I ever build the physical product, which is great because that is something you have to know. And this is why we're going over this, right? Because some of our parts will be more sensitive than others, meaning that some of them we have to be more particular about the voltage rating because they might dissipate more energy than the rest, okay? So, typically things in the signal path, like let's say this pull down resistor here, this grid resistor here, they're not going to draw any current, right? There's not going to be any voltage or current there. Same thing with the tone stack, right? But when you have things like this plate resistor, for instance, this plate resistor and this cathode resistor, if you're going to do a cathode biased amplifier, that's the thing that's usually going to draw the most current. And it's usually going to be a 5 watt plus resistor there. Even probably 10 watts even if you want to do if you're going to use the same resistor to do a pull push and operate two tubes off of one resistor, which is typically actually kind of frowned upon. You don't want to use separate resistors, but for that reason, because of the current draw is going to be so high. So in this particular circuit, what draws the most current is this cathode resistor here and this 100 ohm or this 100K resistor here. Now this one's drawing 1.2 watts, which again is not that high, but it's higher than I expected. And again, having a program like this makes it really easy to pick that out. So knowing that, and I know when I'm going through my parts list that I'll mark down on a piece of paper that I need at least a 2 ohm or at least a 2 watt, and I can even put it here, at least a 2 watt resistor for this plate resistor, right? I can go on this plate resistor. This one's only dissipating 31 millivolts, and I mean that's kind of to be expected because this is a cathode follower. It's not drawing a lot of current from the plate. I could do the same thing here and put a wattage rating on this one. So again, so what we're doing here is defining the final values, and I'm going over the parts that I had to change. There weren't many changes. I was able to find the values that I wanted. Even this 39K, which I thought might have been an off number, but they actually do make 39K resistors. You know, most of the other values are pretty normal. 220K normal, 20K is normal, 4.7K is normal, 33K is normal, 470 ohm normal, 100K normal, 68K normal, 1 meg normal. I did have at the beginning in this power supply a 0.1 ohm resistor, but the supplier that I'm going to just didn't have that. It was okay because this is fairly negligible. These resistors here aren't doing as much for voltage suppression or anything like that. They're really there for noise cancellation, so to just help out this low pass filter that we're creating here. So I have a 10 ohm resistor here, and I can also, this is also important to see, I can see the current draw at these resistors, so you want to go over these and see how much current they're drawing. I think this 68K draws the most out of all of them, but it's still not enough to be worried about. I'm doing, with exception of this cathode resistor and this plate resistor, and I believe maybe 1 or 2 parts in the tone control, I'm using mostly 1 watt carbon composition resistors. Okay. So, oh, and just to kind of backtrack from the last video, if you recall, we were going over trying to figure out if we're going to have enough voltage swing, and I left some remarks in the other video mentioning that I was going to try to see if I can get more out of this, and I did end up getting a little bit more. So if you remember, in the last video, I was able to get I was getting about 13 volts peak to peak. Now I'm getting about 17, which is great. And actually, so I'm getting 17 volts peak to peak out of the cathode of this, this 6SN7. That's going to be driving this KT66, so that's good. And actually, through I found a great calculator for the output stage here online, to where I can get the specific values for the resistor I'm using at that cathode. So right here, so it's a tube bias calculator. So you put your KT66 in here, you select your tube, you enter your plate to cathode voltage. That's the plate voltage minus the cathode voltage. So if we go back here, I have 439 at the plate minus, it's going to be 36 at the cathode. So I got 403. That's going to be my plate cathode voltage. So what this is giving you here is it's saying, okay, if that's going to be your plate cathode voltage, then this will be the percentage of the operating dissipation of that tube, depending on how much current it's drawing, right? So if I was drawing 52 milliamps, 52.7 milliamps, then it'll be running at 85%, which is generally considered cool, right? So it's not running that hard. And remember, we're looking for cathode bias, because that's what we're doing. We're doing a cathode bias amplifier. These other values are for a class A, that's fixed bias. That's if we were having a negative supply and putting negative voltage into the grid. We'd be doing it like that. And as you can see, there is a little bit difference in that number. So in a sense, so if you're using a fixed bias, then the tubes generally run cooler. Especially look at this class AB. So if the class AB, they're running, at 50%, and that's the whole idea about the pull-push, right? So this is giving you the pull-push rating. So if you can see, this kind of gives you a glimpse and a good idea of, the difference between pull-push and a single-ended, right? So this cathode bias, which would generally, I think they're giving you, single-ended numbers, is running a lot hotter than your pull-push, especially your class AB, right? So your class AB is running, 31 milliamps and only 50%, which is, I guess, more typical of a pull-push amplifier, because one tube would be running half the cycle, and the other one would be running the other, and that's why they split the duty cycle essentially, so they don't have as much workload as either one. And that's another thing to consider when making these single-ended amplifiers. Now, I've done some research on them, and they say that they sound more airy. They say they actually sound really good with jazz, and they kind of have their own quality. I mean, obviously in the audiophile industry, they are very well reputed. Having single-ended monoblocks are one of the biggest things. Obviously, it's just more expensive, especially in the audiophile industry, to run single-ended monoblocks, but they sound great. So anyway, so we have our milliamperage, right? So we can get an idea about how much current it's going to take and how much dissipation we're going to get and how hard we're driving our tube. So you see at 62, that would be the max safe dissipation. So we don't want to go any beyond 62, and we don't want to really go any lower than I'd say 55 or 52.7. But it really just depends on how we bias this thing. So going forward, see, enter the number of tubes that share the cathode resistor. That's only one, and the voltage drop across that resistor is 36, and it's a 600 ohm. All right, so that's going to show you the cathode current. This is why this calculator really works out great, because it shows you the cathode current. So you had 60 milliamps, which even if we go on we can verify these numbers, which is what's great about this, is we can cross-check these numbers with this website and the SPICE model. So this is saying if we have 403 volts at our plate cathode voltage and a 600 ohm resistor, then we'll have 60 milliamps at our cathode, and that actually checks out to be correct, because we can go here and look at our cathode current here again, and we have 60 milliamps, 60.9 milliamps dissipating 2.2 watts. So the calculator is accurate. Now for the total plate current, it shows 56. And if we remember the power supply, the power transformer I'm using supplies 71, so we should be good there. Now it's showing the total plate dissipation, which is one of the facts that we're most interested in, which is 22.9. So that would indicate that we're going to be operating this thing a little bit hotter than we need to, right? So we're doing 15 watts. If we're doing 15 watts at 22, it means this tube's going to be running a little bit higher but that's also good because it will give us a lot of headroom, right? So we'll be running it at 91%. So this gives us some good numbers and gives us a good idea about where we're going to be operating at. So that 91%, if we go back up here, that's about average, right? That's about average it's a little bit below average for a cathode bias, single-ended tube. Tone control circuit is something else I had to go over. So the way to do this, another way to do this is actually to use, I think Duncan supplies a tone control stack calculator also. So with this tone stack calculator, you can pick out different circuits and do a frequency sweep of them. And they've had one here that was already built in that's just about perfect for the operation I want in this amplifier. See, it's got a mid scoop at 100K kilohertz, 1K kilohertz. And you can also do a sweep of the whole circuit, right? So we can see where it cuts off the highs and where it cuts off the base, right? So it'll take the base almost all the way down to negative 20 dB, and it'll raise the highs up to 0 dB. Now we can clear that and do. You can also sweep as if this would be the potentiometer, right? So we can look at what our potentiometer is doing, right? So I would say usually I'd probably operate somewhere around there, right? So I'd raise my bass up and then lower my treble just a little bit. So this left side or this right side would be the treble. The left side your bass here, and you can kind of get a good idea of what your frequency sweep would be. Now, obviously, you can go in here and also change the values. I don't know. Let's say if I wanted a larger mid scoop, then I can do that as well. But I actually like the values that were already in it. Let's see. I guess you could lessen that mid scoop. So what we're doing here is this capacitor here is what's really going to control the low pass filter. So this is the low pass filter up here, down here, and this is the high pass filter. So I've kind of just flattened out that curve, putting a 5 nanofarad instead of a 10 nanofarad capacitor here, and that's what that does. So it's lessened the mid scoop there, but all the other results are basically the same. So, but anyway, I'm just showing you what this can do. Like I said, again, because of technology and all that, there's so many useful tools to help you in aiding getting into electronics or building amplifiers or whatever the case may be. Oftentimes I find it even difficult to just sit there with a pen and paper sometimes, because there's so many great tools online that'll give you so much information about the amplifier before you even build it, to the point where you have to do very minimal testing and very minimal mock-ups and revisions when you make it. And that's why we're doing all this, right? So the more diligence you do, the more due diligence you do in the process of designing, the less you'll have to do in revisions, right? So, and these calculators and things like this just make it all the more accurate. So that's pretty much where we're left off. Everything's looking really good. Like I said, I've got the majority of the parts already in Tubes and More, Antique Electronic Supply. I've been itemizing everything, and we're well on our way. Another modification I made was using an 8-inch speaker instead of a 10-inch, because I'm trying to make this thing small. So whatever it takes to just make it small and compact is what I'm going to do. But aside from that, that's where we're left off. We've got the values. I've got figures on what my output's going to be doing. It's going to be getting 17 volts in, and it's going to be producing about, I think, what was it, 22 watts output, which is about 7 watts over what we actually need. So that's great. It's going to be running hot, but not above its capability, and that'll give us a lot of headroom. So it should be a nice, real good, clean sounding amp. As you can see here, we've already got our waveform for our sine wave going into our preamp signal, and that sine wave couldn't be any cleaner, right? So just as a note, if it wasn't clean, you'd see some oscillation or some breakups here. You'd also see your biggest indicator for clipping and things of that nature is going to be a flattening out at the top or the bottom, right? So if you start to see these peaks or these curves at the top start flattening out, then that would mean that that you're getting some distortion, you're getting some clipping, right? So right now, all our signals look good. The parts that we've selected are looking good. We've got an idea of, which parts need to be bigger, what wattages the resistors need to be, so we won't run into any overheating problems. Again, this is why we want to do all this, because you want to have the least amount of problems when you construct it. Usually you don't really want any, right? You just want it to be kind of a one and done kind of deal, right? And doing diligence like this really helps. So knowing what wattage your cathode resistor needs to be, what wattage this plate resistor needs to be, that's going to help immensely in organizing your parts. So when you build it, you won't have any problems in overheating and things of that nature. That's also why we were so diligent about trying to figure out the current consumption from our filament of the tubes, as opposed to in relation to the power transformer, because we don't want to overload things, and we want everything to be working correctly, right? So what's really great about LT Spice also, that it'll give you a bill of materials, so you can actually see all of the components here and get an idea of all the components that you'll need to build this thing. So you can actually just make a bill of materials here and print it out and just start ordering from this list. I believe you can also send it out to suppliers. I believe I think other CAD and Spice programs let you do that. I'm not sure if LT Spice, I'm sure it probably does. But you can actually, you can put manufacturers in here and parts numbers and all that kind of stuff. So, but yeah, that's what we're left with. So the next part, I'm just going to be ordering these parts, and while the parts are getting here, I'm going to start drawing out or mapping out, or just building the physical, or getting an idea of how I'm going to build the physical product. So how I'm going to build the chassis and the layout of this thing, all right? So that's where we're at. Thanks for watching.